One of the tested skills of Math M that students find pretty challenging on a regular basis is the skill to graph functions. You know the questions I'm talking about. The question opens with a function that you're given, and then there's a litany of things that you're asked about that function. What is its domain? What are its intercepts? Does it have any discontinuities? Where are they? Asymptotes? What's the limit behavior like of this function? Where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? And then the final question in that long line of questions is, please sketch a graph of this function. And somehow it's really difficult to put everything together, but it's so necessary to take all these pieces of things that we've learned how to calculate. First derivatives, second derivatives, intercepts, limits, all of it, to synthesize it and put it into a picture to understand what that function might look like is certainly a very important skill to have under your belt. And as we've moved through Math M and we've been introduced to all different types of new functions, such as trigonometric functions, things of that nature, and all kinds of derivatives that we're now able to take, this tested skill that began in Math MA with exponentials and logarithms and things like that continues to be an important one. And this video is supposed to help you approach those questions, maybe help you organize your thoughts with some helpful tools, tips, and maybe some common pitfalls that students encounter. So before we begin with these practice exam questions, it's important to think about all the different things that we are being asked to find. Let's take a look. Most of the questions begin by asking where the function's defined. What is its domain? This can also tell you where there are holes or asymptotes, or simply where the function does not exist. Usually that's followed by intercepts, where x is equal to 0 or y is equal to 0. And then that's followed by limit behavior. What's happening as x is going to positive infinity or negative infinity, or perhaps if it has a truncated domain. Maybe it's only positive numbers. Well, what happens as it approaches 0? If it has any asymptotes, say it has an asymptote at 2, what happens as it approaches 2 from the right? What about from the left? Then the questions sort of turn to the first derivative. Yes, on the surface, it's also asking you where the function's increasing, where the function's decreasing. Those are usually the questions that are being asked there. But more importantly, the first derivative can also shed light on local maxima and minima. Similarly, while the second derivative can answer questions of concavity, where is the function concave up, where is the function concave down, it also will tell us where there are inflection points in the function. And last but not least, occasionally, you're asked to say whether the function is even or odd, if there's some sort of symmetry happening. And then the question is, how do you put everything together into a picture? We're going to talk about this with some tips. The main issue is that students fail to adequately combine the information about the first derivative and second derivative, even if they have found that information correctly. Again, like I said, the first derivative is not only going to tell you increasing and decreasing, but maxima and minima. The second derivative is not only going to tell you concave up and concave down, but also points of inflection. And it's together in a single table that the first derivative and second derivative will combine to give you an idea of a rough shape of the function. Combine this with the necessary maxima and minima that you know, the intercepts that you need to go through, and the limit behavior that you need to obey, and you'll have a nice picture of this function. As you work through some of these future problems, I think the major point is to always approach these problems the same way. Organize your work in the same way. The better a scaffolding that you can build for your work to sort of form onto, the more reliable it is on the exam for you to replicate it there and get full credit or close to it on the final. The first function we're going to be looking at is e to the root x over root x. And right off the bat, our number one question is, what is the domain of this function? What are the possible input values that we could put in? Now, anytime we're plugging in root x, it's underneath a square root sign. And that function, that square root function is what is going to disqualify some inputs from being useful. Now the square root function only accepts inputs that are 0 or greater, so there's that. But then there's also the fact that our denominator cannot be 0. So 0 can't even be an input for x because it would make this function undefined, since that would leave 0 in the denominator. So that leaves us with a domain that is strictly positive, as in greater than 0, it cannot be equal to 0 because the denominator cannot be equal to 0. And so in interval notation, that is going to be 0 non-inclusive to positive infinity. I've included a little bit of justification so that you can follow along. So square root function in general means that x has to be greater than or equal to 0, but for this particular function, x itself cannot even be equal to 0 because of that square root function in the denominator. Now, for what values of x in the domain of f is f increasing? Of course, this now translated into calculus speak is asking, where is the derivative positive? Before I even calculate f prime, I like to re-express f as a product of two different functions rather than a quotient. Let's do that. Note that for computational ease, I've also elected to express square root of x as x to the 1/2 power. So let's use the product rule on this thing, shall we? Here I've done my best to take the first derivative of this function. I use the product rule, so this is the derivative of the first term, right, using the chain rule on that x to the 1/2 up in the exponent, leaving the second term alone, and then adding on, leaving the first term alone, taking the derivative of the second term. Now let's sort of algebraically massage this, simplify it a little bit just to get into a nice, more palatable view. Now let's try to combine this over one single denominator. The common denominator is going to be 2x to the 3/2. All we have to do is multiply this term by x to the 1/2 over x to the 1/2. All right, now this is something that I actually want to analyze. Now we need to remind ourselves that x is strictly positive. That means that the denominator here, 2 times x to the 3/2, is also strictly positive, so it has no bearing on the sign of f prime. That means that we can basically analyze the sign of f prime by looking only at the numerator. So let's do that. This is x to the 1/2 times e to the x to the 1/2 minus e to the x to the 1/2. Common factor of e to the x to the 1/2, let's factor that out. And there we go. We essentially we just want to know sign, right? So we basically want to know, when is this numerator positive? The denominator is always going to be positive. So when the numerator is positive, this whole thing will be positive. When the numerator is negative, this whole thing will be negative. So we basically want to know, where's the numerator 0, and then we'll test points on either side of that. Well, when is this equal to 0? That's an interesting question. This is a product of two terms. And when a product of two terms is equal to 0, that means one or the other of them is going to be equal to 0. So let's see when either of those things happen. The first term is e to the x to the 1/2. Well, e to anything is actually never equal to 0. So this can't be the culprit at all. The only 0 that we can possibly get is from x to the 1/2 minus 1 being equal to 0. X to the 1/2 minus 1 being equal to 0 happens when x to the 1/2 is equal to 1, which means that happens when x is equal to positive 1. Perfect. That gives us a critical point. Let's put it on a number line. Now let's test points on either side. Let's pick something that's less than 1. Now remember, our domain is strictly positive, so it has to be strictly positive with less than 1, so let's pick something like 1/2. Well, if we pick something like 1/2, what happens to the sign of our derivative? Again, denominator of the derivative is always positive. The numerator, however, let's take a look at this writing of it. This will always be positive. X to the 1/2, well, when we take 1/2 to the 1/2, we're trying to take the square root of 1/2, so that's 1 over square root of 2. Still less than 1, right? We subtract 1 off of that, that's going to be negative. So we have positive times negative, which is going to be a negative value, meaning that the function itself is going to be decreasing. Now, if we pick something that's greater than 1, something like 2, right? Well, e to the 2 to the 1/2, that's always going to be positive again. Root 2 is greater than 1 minus 1/2, or pardon me, minus 1. That's going to leave us with something positive. And of course, the second that we get something greater than 1, its square root is going to be greater than 1. And this term right here will be positive. So we know that for something greater than 1, it will be positive. What does that mean for the function? Well, it means it's decreasing here and increasing here. So that's the behavior of f. That down here is the behavior of the derivative. All right, moving right along. I guess we should probably write out our formal answer, which means that where is it increasing? Well, it's increasing for values greater than 1. It's not going to become negative anywhere else. Second question is a limit question, and it's not surprising, right? It's asking us, what is the limit as x approaches infinity, as it extends into its domain forever and ever? We note that if x grows without bound, the denominator and the numerator both grow without bound. We have an infinity over infinity indeterminate form, which means that we want to use L'Hopital's rule. L'Hopital's rule says that the limit of that first indeterminate form is going to be equal to the limit as x approaches infinity of the derivative of the numerator over the derivative of the denominator. So let's compute those. After successfully computing either derivative, remember, just take the derivative of the numerator by itself and stick it in the numerator. Derivative of the denominator by itself, stick it in the denominator. Don't confuse yourself with trying to adjust negative exponents into or out of the numerator and denominator quite yet, because we can see that we have a common factor of 1/2 x to the negative 1/2 in both the numerator and the denominator. This will cancel out. And what we're left with is the limit as x approaches infinity of e to the x to the 1/2 power, or e to the root x. So the limit as x approaches infinity is just going to be infinity. So we've learned quite a lot off of this page. Let's take a look at the second half. We're now being asked to figure out what's happening on the other side of the domain. Remember, our domain was strictly positive numbers, not inclusive of 0 to positive infinity. We figured out what happens as we go to positive infinity. We want to know what happens as we approach 0 from the right. Let's try it out. As we approach 0 from the right, e to, well, root x. If x is approaching 0 from the right, root x is also approaching 0 from the right, and e to the root x is approaching 1. Now, the denominator, right, root x, well, if x is approaching 0 from the right, root x is approaching 0 from the right. So we have something that's going towards 1, that's finite, small but finite, and something that's approaching 0 from the positive side. This means that this limit is going to be positive infinity. Our final step is to sketch a rough graph of the function. We want to take a moment and write down every single characteristic of this function. First, its domain. Then, where is it increasing? Then, what is its limit behavior in either direction? We might take a moment and pause and think about this and whether it has any intercepts. E to the root x over root x, well, we know the inputs can only be positive, and e to the root x actually cannot be negative at all. Neither can the denominator. So the whole thing's positive. It's in fact never even equal to 0, right? So it's all above the x-axis. When we realize that it's decreasing from 0 to 1 and increasing from 1 to infinity, we can actually take a moment and synthesize that fact into the fact that there's a minimum at x equals 1. And it tells us that we don't even care about the concavity, but we can just sort of sketch it ourselves. I know that it has to go upwards as it approaches 0 from the right. So it's going to go up that way. It's also going to go up towards infinity as x goes to infinity, but it's going to have a minimum at x equals 1, where it goes from decreasing, to increasing. So we have x equals 1 there. So putting that all together, right, it should go up like that and up like that. And that's it. The rest of this problem has to do with actually integrating this using substitution, but this was the part that focused on actually drawing the graph, which is the focus of this video, so we're going to stop right there.
Our next function that we're asked to take a look at is this one, x over e to the x squared. And just like always, well, at least most of the time, the first question on our mind is what is in the domain of f? So that means what inputs are allowed here? Now, unlike in our previous function where we had a square root function which was going to limit the domain, as well as a square root function in the denominator that was going to limit the domain, we don't have that here. In the numerator, we have x. Well, we can input x to anything, right? X could be anything. That could be negative, positive, 0, it doesn't matter. And in the denominator, we have e to the x squared. Now, x squared in the exponent. You can put in negative or positive numbers. You will always come out with a positive number once you square it. So we're taking e to a positive number, and our major concern is basically checking to see whether the denominator is ever equal to 0, in which case the entire function would be undefined there. Well, e to any exponent, no matter what its value, would never be equal to 0. And so there's no restriction in the denominator either. The domain, as it happens, is going to be all real numbers. Our next question is an interesting one that you should always ask yourself regardless of whether or not it's explicitly asked of you, because it can provide a way to double check pretty much most of the rest of the work for this problem as well as the final answer. Let's take a look. It says, is f an even function, an odd function, or neither? Now the way to determine this is to plug in negative x and compare what you get to the function f of x. Well, as we plug in negative x down in the denominator, it is being squared. So e to the negative x squared is equivalent to e to the x squared power. Let's rewrite it that way. And now we can really analyze this. What we have here, I removed the parentheses in the numerator, is negative x over e to the x squared, which, since f of x was equal to x over e to the x squared, this is negative 1 times f of x. This relationship, the fact if you multiply an input by negative 1, you're multiplying the output by negative 1 as well, is the trademark of an odd function. That's a bit of review, right? Back from MA. An even function would be that if you multiply an input by negative 1, there is no change in what's coming out on the other end. But this is the trademark of an odd function, and we want to maintain that understanding throughout the rest of this problem. Now here comes some of the computation. For what values of x in the domain of f is f increasing? Well, it's nice for them to remind us that these values need to be in the domain of f, but that's really more significant if the domain was limited in some way. We are not limiting our domain at all. Our domain is all real numbers. So we're looking for any real number for which f is increasing. And of course, the first thing that we note is that this question in calculus speak is asking us, when is the derivative positive? So what we want to do is compute that derivative, find where it's equal to 0, and then test points in each of the intervals among these critical points to figure out where is it positive, where is it negative. Not only is that going to tell us where it's increasing, that's going to tell us where it's decreasing, that's going to tell us where there are local mins and maxes as well. The first thing I like to do here is I like to rewrite this quotient as a product because, well, I'm pretty much allergic to the quotient rule. There's just more computation in it. I sometimes misremember it. It becomes challenging for me, but that's a personal preference. You're more than welcome to use the quotient rule on this function, but I'm going to use the product rule. So here we go. I've also decided to rewrite the question so that I know exactly what I'm trying to answer here. Upon first pass, here's my attempt at writing down this derivative. What do we have? Well, I take the derivative of the first term x, leaving the second alone, right? So now I have 1 times e to the negative x squared, plus leave the first term alone, take the derivative of the second, so x e to the negative x squared times negative 2x, because that's the derivative of what's in the exponent. We need to use the chain rule there. Now we want to combine some of these. Of course, we're trying to figure out where the first derivative is positive. But before we get to that destination, we want to figure out where the first derivative is 0. Because we really want a full picture of this, right? We want, where is it decreasing, increasing, max, min. We know that we're going to have to sketch this graph. And so, yeah, it's great for the purposes of this question for answering where is it increasing, but I also want to know sort of what's happening everywhere else. So we want to figure out where is it 0. And the first thing to do there is to note that there is a common factor in both terms, right? It's e to the negative x squared. Let's factor it out. And so now this is great because I want to know where this is equal to 0 to find critical points. We have a product of two terms, e to the negative x squared and 1 minus 2x squared, and their product is 0, so one of them has to be 0. And we mentioned already that e to the negative x squared, right, that can never be 0. It is always positive. No matter what you raise e to, you will get a positive number. But 1 minus 2x squared, that can give us a 0. So when will 1 minus 2x squared be equal to 0? Let's figure that out. And we find two critical points, positive and negative 1 over root 2. Well, it's interesting that we find two critical points, one that's positive and one that's negative, that are the same magnitude. And in fact, that shouldn't surprise us, right? Because this is an odd function, right? Where there's a min on one side, there should be a max on the other, and vice versa. So where the first derivative is equal to 0, if there's a positive value, there should be a corresponding negative value for that. So now let's take a look at what our number line looks like. We want to mark these critical points, 1 over root 2 and negative 1 over root 2 on there. Now I know that 0 is not a critical point at all, but I just put it in there so I sort of understand my number line pretty nicely. And I want to check each of these various intervals on that number line. Now let's pick something that's less than negative 1 over root 2. So I'll pick something like negative 2. Now if I plug in negative 2 into f prime, we can say right here, well, I know that e to the negative x squared, doesn't matter what you're raising e to, always going to be positive. 1 minus 2x squared, well, negative 2 squared is 4. 2 times 4 is 8. 1 minus 8 is going to be negative. So we have something positive times something negative. So over here, right, we have a negative sign for f prime. I'll even write in what I'm talking about right here. How about in between negative 1 over root 2 and positive 1 over root 2? Like say we're at 0. Well, again, e to the 0 will be positive. 1 minus 2 times 0, well, that's just going to be 1. So we have positive times positive, so it will be positive there. All in between negative 1 over root 2 and positive 1 over root 2. And what about greater than 1 over root 2? Well, plugging in something like positive 2, we end up with the same issue that we had with negative 2, right? Everything is squared when it comes to x in here, so we actually end up with another negative over here. And of course, what does that mean for our function f? This means that it's decreasing from negative infinity up to negative 1 over root 2. Then it's increasing between negative 1 over root 2 to positive 1 over root 2, and then it's decreasing again. So it is really important to note here that we have a min at negative 1 over root 2, and we have a max at positive 1 over root 2, and that is typical of odd functions. Like I said, you know, some people like to say, oh, you take the function from 0 to infinity and you reflect it over the y-axis, and then you reflect it over the x-axis. That is true, but also every max from 0 to infinity, if you take that input and multiply it by negative 1, you'll be at a min on the other side in an odd function. So this is in keeping with that. And of course, we always want to remind ourselves, what was the original question? We want to know, for what values of x is f increasing? Well, it's just going to be from negative 1 over root 2 to positive 1 over root 2. So that's our official answer, but we really do need all of this other information. All right, as is typical, we want to know what's happening as we approach the limits of our domain. So it says final limit as x approaches infinity of f of x. So we're asking, what's the limit as x approaches infinity of x over e to the x squared? And of course, upon first look, the numerator is growing without bound. The denominator is also growing without bound. And so we have an infinity over infinity indeterminate form. And this should trigger in your mind L'Hopital's rule. So this means that the limit as x approaches infinity of x over e to the x squared will be equal to the limit as x approaches infinity of the derivative of x over the derivative of x squared. It's really important to realize that those limits are equal, not that the limit is equal to the derivative of x over the derivative of e to the x squared. The limit is equal to the limit of the derivatives over each other. And this is very exciting. Anytime I do L'Hopital's rule where I have a polynomial in either the numerator or denominator, that's great to me because I know that the derivative will eventually disappear, go to 0, or at least go to a constant. So this one iteration of L'Hopital's rule leaves me with the limit as x approaches infinity of 1 over e to the x squared times 2x. The denominator, of course, is growing without bound. The numerator is 1, so we have 0. Now what's interesting to think, though, is that, well, if we're approaching 0 in the limit as we move all the way out to positive infinity, if we reflected that over the y-axis and then reflected it over the x-axis, we'd still be approaching 0 as we move to negative infinity. So it's just good to remind ourselves that even though the question's not asking us the limit as x approaches negative infinity of f of x, that will also be 0. And in fact, that little piece of inference is really important for this next question. The question asks us, does f have an absolute max on negative infinity to positive infinity? If so, what x value does the absolute max occur on? Well, we remind ourselves that at either end, as we're moving towards negative infinity or positive infinity, the function's going to 0. So it's not growing without bound in either direction or decreasing without bound in either direction. And so those local mins, there was a local min at negative 1 over root 2, and there was a local max at positive 1 over root 2. And in fact, those are going to become absolute maxima and absolute minima. Of course, this question is asking us specifically about absolute maxima. But the fact of the matter remains that because of the limit behavior, there is going to be no other moment where the function is going to overtake the function value at positive 1 over root 2. So the part that's boxed is the relevant work for the correct full solution credit or whatever, but the part in parentheses is my justification for that. I'm taking a look at what happens in the limit at either end. I'm looking at the behavior of the function, sort of in the central part of the function value. I have these two, local max and local min, and the fact that beyond that, the function just tapers off to 0 means that those are going to be absolute maxima and minima as well. So now our job is to sketch a rough graph of f. Our graph should reflect what we've done in the problem, but we don't need to accurately show the concavity. Now I want to put, again in bullet points, synthesize everything that we've done so far. First thing is, the domain is all real numbers. Next, it's an odd function. It needs to reflect over the y-axis and then reflect over the x-axis. We also know that it's going to be decreasing up until negative 1 over root 2. I pretty much like to copy the sign chart itself in its entirety over here. Let's take a look. That's what it looks like. And of course, this is going to be an absolute min. And positive 1 over root 2 will be an absolute max. Now, what's left for us here is to sort of, you want to separately think to yourself, when will this be positive? When will this be negative? When will it be zero? Right? Well, the fact of the matter is that regardless of your input, the denominator is always going to be zero because e raised to anything will be positive. And so the numerator is controlling the sign. The numerator is saying, hey, I'm in charge, right? When the numerator is zero at x equals zero, the function will be zero. When the numerator is positive for all x greater than zero, then it will be positive. When the numerator is negative for all x less than zero, the numerator will be negative, or the whole thing will be negative, pardon me. And last but not least, we also have our limit function, right? So the limit, as we move from either towards positive infinity or negative infinity, it's going to be zero. Now note that with odd functions, usually if the limit is something that's non-zero, like, oh, the limit as we go to positive infinity is positive infinity, that means that the limit as we go to negative infinity would be opposite sign, right? Reflected over the y-axis and then over the x-axis. But in this case, zero doesn't have a sign. So limit as we go to positive infinity is zero, limit as we go to negative infinity is zero. Now we have to plug all of this in. So here I've put our two major moments, our absolute min and absolute max, onto the axis already. I know that I'm going to have an absolute min there. I know it's going to increase, and I know it's going to be zero when x is equal to zero, and then it's going to increase to the absolute max. So it looks like that, right? We're increasing between negative 1 over root 2 and positive 1 over root 2. Then we're tapering off to 0 over here. So this is going to just go down like that. And then similarly on the other side, right, exploit the odd nature of the function. Reflect over the y-axis, then over the x-axis, and we end up with something that looks like that. And that's it. That is our graph that reflects everything we've done in the problem. It's an odd function. It's increasing and decreasing where it needs to be. The limit behavior is exactly what it needs to do, and it has absolute extrema where it needs to as well. The remainder of this problem involved integrating this particular function, but I'm not going to go into that because this focus topic is really on graphing these functions. Our final function that we're going to look at is cosine x minus sine x. And right off the bat, we're being asked, does f have an absolute maximum value? If so, find it. If not, explain why not. Well, looking at this function, I know that it's going to be pretty repetitive, right? I'm looking at cosine x minus sine x. Both cosine and sine cycle between -1 and +1. I'm not really sure what the difference is at any particular moment, but the fact of the matter remains that if we're going to have an absolute maximum, my suspicion is that this will happen an infinite number of times whenever x equals something in particular. Same way cosine by itself does have an absolute max at +1, but there are an infinite number of inputs where that absolute max is achieved. So let's see, when it says absolute maximum value, I need to know what the first derivative is. I also need to know what the second derivative is so I can figure out which ones are maxima and which ones are minima. So let's get to it. First derivative of f. Now, of course, we're just following our hunch that there are an infinite number of absolute max and mins. So our first question is, where is this equal to 0? And we can solve for this x. We can bring negative sine x onto the left-hand side by adding, right? So we have sine x equals negative cosine x. And then we want to remind ourselves of the unit circle. Now, we're very familiar with the unit circle, and we know that there are places in every quadrant where the magnitude of cosine and sine are the same, right? That's pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 in one lap around the unit circle. But of course, we're not just asking that the magnitude be the same, we're asking that the magnitude be the same, but the sign be opposite. And so that happens here in this quadrant where sine is positive, but cosine is negative. And it happens here in this quadrant where cosine is positive, but sine is negative. So our two possible solutions for this are that x could be 3 pi over 4 or 7 pi over 4. And of course, 3 pi over 4 plus 2k pi, right? Every single time we pass by that place on the unit circle. And same thing for 7 pi over 4. All right, so we have these two critical points we need to figure out if they're maxima or minima. I'm going to prefer the second derivative test just because the second derivative seems like it would be really easy to take here. And just to remind ourselves exactly what we're testing, I'm going to use a little number line, as we did with pretty much every other problem, right? Here's my number line. I'm looking at 2 pi multiples of 3 pi over 4 and 2 pi multiples of 7 pi over 4. And I want to test the sign of the second derivative at these particular points. So quickly do that and we'll see what happens. How do we do this? Well, we take 3 pi over 4, we plug it in here, we say, okay, negative cosine of 3 pi over 4. Well, cosine was already negative over here, so negative cosine is going to make that positive, plus sine, well, sine was positive, so here the second derivative is going to be positive. How about at 7 pi over 4? Well, cosine there was positive, so negative cosine is going to be negative, plus sine, which was negative. So we have a negative number plus another negative number, which means we're going to have a negative number. 11 pi over 4 is the same location in the unit circle as 3 pi over 4 was. So the second derivative is going to have the same sign there. And 15 pi over 4 is the same location in the unit circle as 7 pi over 4 was. So the second derivative will have the same sign there. But what's important is that we now have the sign of the second derivative. And so what we know here is that where the second derivative is positive, we have a min. Where the second derivative is negative, we have a max. And so we have a whole bunch of mins and maxes forever and ever and ever. The points that are in the same location of the unit circle as 3 pi over 4, those are the mins. And the same points that are in the location of the unit circle with 7 pi over 4, those are the maxes. So we've basically done all of the work necessary for both A and B up here. So it does have an absolute maximum value. Note that when we talk about absolute maximum values, we're asking what is that value? So we know what happens at 7 pi over 4. We want to know what is the function value at 7 pi over 4. Here we find that cosine 7 pi over 4, which is root 2 over 2, minus sine of 7 pi over 4, which is negative root 2 over 2, subtracting a negative number is going to be equivalent to adding these numbers together. So we have 2 root 2 over 2. And so the 2's will cancel, right? We're left with root 2 as our maximum value. That's the max value. Does f have an absolute minimum value? It does. We figured that out here, right? There are no discontinuities in this. There are no asymptotes. This is a function that oscillates. That was our hunch, and all of our analysis has confirmed that. And now instead we're looking at the particular inputs that live in the same place on the unit circle as 3 pi over 4. So let's find what the function value is there. And negative root 2 over 2 minus root 2 over 2 is negative 2 root 2 over 2. So those 2's are going to factor out there. And that is our minimum value, negative root 2. Most of the work was done up here when we were analyzing the first question. And then this just sort of fell right into place. We're being asked to sketch a rough graph of f. We're told that we don't need to verify that it's sinusoidal. We're told that, but it was a good hunch, right? We want to keep in mind that it's a sinusoidal function, and it says be sure to label your axes clearly. So it's pretty clear to us that we want to make sure that our particular important points are there, 3 pi over 4 and all of its multiples, and 7 pi over 4 and all of its multiples. So let's label the axes first. Now, from our analysis on the previous page, we know where there's maxes and mins and things like that, but we might want to know where there are zeros, and that's actually quite straightforward because we can totally do that with this problem. So over there in the corner, I kind of scratched it out. I said, hey, where are the zeros to this function? Well, the zeros are where sine x and cosine x are equal. And we can remind ourselves that that is going to happen at 2 places on the unit circle. One is up here in the first quadrant at pi over 4, and one is down here in the second quadrant at 5 pi over 4. And so that means that we can basically space this out pretty nicely. These zeros are going to happen right in the middle of each of these intervals that we've already labeled. You also may have, when I unveiled this tick mark system, freaked out a little bit, like negative pi over 4, negative 5 pi over 4, negative 9 pi over 4, where did those come from? These are the reverse. When I take 3 pi over 4 and I subtract off 2 pi, I'm going to get negative 5 pi out over 4. When I add 2 pi, I get 11 pi over 4. 7 pi over 4, when I subtract off 2 pi, I'll get negative pi over 4. So these are just other integer multiples of these mins and maxes. So as we have already deduced the 7 pi over 4 plus any integer multiple of 2 pi, those are the maxes. The 3 pi over 4 and any integer multiple of 2 pi, those are the mins. When we connect everything together, what do we get? A nice sinusoidal function. Going through the zeros we want, hitting those maxes we want. And there we have it. This is our rough graph. The maxes are achieved at 7 pi over 4 plus 2 pi multiples, integer multiples, and that function value is root 2. The mins are at 3 pi over 4 plus 2 pi multiples, and the function values are at negative root 2. And the remainder of this is just a trig question to try to figure out another formula for this. But this is a fantastic opportunity to take a look at mins, maxes, use that information about the first derivative, so on and so forth, and keeping all that information very clear in our minds. As always, if you have any questions at all, please don't hesitate to ask, and happy studying.